Welcome to GEOGR485 585L, Internet Mapping, Module 5.2, Developing and Hosting OGC Services, OGC Services and Styling in GeoServer, Part 2. This week we are going to continue our discussion of styling using styled layer descriptors in GeoServer with a focus on styling raster data, as a complement to our previous conversation about styling vector datasets. So as a part of today's presentation, we will first review the overall concept of styling in GeoServer as it relates to rasters, and then we will go through some examples of different capabilities within GeoServer for styling raster data. So if we start with a brief review of the raster symbolizer within GeoServer, you might recall that we have a number of elements within the styled layer descriptor capability that you can use to modify how a given raster dataset should be displayed. And those elements include an opacity element for controlling the opacity of the entire data set through setting a value from 0 to 1. A color map element where you can define the type of color map and also the color range that is used by that color map, where that color map then contains one or more color map entries that define specific colors, values in the raster, an optional label, and opacity that can be defined at the level of a single value within the color map. We can also use the channel selection element to correlate specific channels in a multi-channel raster dataset to the red, green, and blue channels that GeoServer would use to render a map image, and also specify if we only want to designate a single channel from a multi-channel dataset as a gray level channel that GeoServer would use for rendering a map image. Finally, we have some capabilities within GeoServer relating to the contrast enhancement element, where you can, within the contrast enhancement element, modify the mapping of the range of values within a dataset to the range of colors that are depicted in a map. This is a way of typically increasing the contrast or the range of values from lowest to highest for a particular dataset, or also brightening an image using another option within the contrast enhancement that we will talk about. We will be focusing on these 4 key areas for specifying how raster should be rendered, keeping in mind that the Open Geospatial Consortium styled layer descriptor specification includes 3 other elements that are not implemented within GeoServer and will not be included in our discussion today, those being shaded relief, overlap behavior, and image outline. Starting with a set of examples relating to the color map element for specifying the range of colors as they are assigned to different values within a raster, we will start with a sample styled layer descriptor, as you can see here, as the basis for working with and illustrating the effects of some of the options for defining color maps and their settings. Keeping in mind that we're following the same model we used in our previous discussion about GeoServer styled layer descriptors, where in this case we are only providing the portion of the SLD that includes the named layer element and all of its components. We do not include in this sample the XML header or root tag or root element for the complete SLD. Looking at the color map element in particular, we can see a number of features. First, in this initial sample SLD, we have not specified any options for this color map. That means that it will use the default values that GeoServer has identified for the color map element, with those corresponding with a type of ramp. So where type equals ramp, and we'll see some examples of that in the next few minutes. And also extended equals to false, meaning that the color ramps that are going to be generated by GeoServer will be limited to 256 colors. These are the default values, and if you do not specify them explicitly, those values will be used when you use an otherwise unmodified color map element. You can see that this color map element then contains a number of color map entry elements, each of which contains a specified color, where the color is defined using a hexadecimal color notation, for which there are a wide variety of online references for how you can correlate a desired color to its hexadecimal representation, where in this case, this numeric value of 6 zeros corresponds to black. And if we go down here, this hexadecimal representation of all Fs corresponds to white, and all of the intervening values represent colors or shades of gray in between those two extremes. Each color map entry also contains a quantity attribute, where you specify the raster value that should be assigned to that particular color, where the visualization of that relationship will depend upon the type value of the color map itself, and we'll be talking about that more in a few minutes. You can also provide a label for each color map entry that can be used in a map legend that is automatically generated by the resulting services that are hosted by GeoServer. And you can also optionally provide an opacity value for each color map entry. So this is as a complement to setting an opacity value at the level of the entire raster symbolizer, as we see here. We can then also set an opacity value at the level of a single entry in the color map that we're defining. This gives you a high level of granularity in terms of even controlling transparency of features within a particular class or range of values, while the rest of the map might be entirely opaque. Here we see an example of the default ramp type of raster color map. And you can see that this can be represented in two ways within a styled layer descriptor that GeoServer will use. You can first use a simple color map with no additional attributes, where the ramp type is then assumed as the default, or you can explicitly define the color map as type equals ramp. Both of these represent a situation where each of the color map entries represent a point along a continuous gradient of values. So GeoServer calculates the intermediate colors between each of the colors defined for each color map entry and interpolates those to have essentially a wide range of values that are associated with the raster that is being displayed. So again, a ramp is ultimately represented by a continuous gradation of colors with some anchor colors defined by the color map entries. In contrast, we can look at an intervals type of color map where you define that simply by choosing color map and setting the type attribute to intervals. And in this case, when you are using an intervals color map, you are telling GeoServer that you want to use only the colors that are defined in the color map entries, and that any of the values that are between one color map entry and the next should be assigned to the previous color map entry until the next value is encountered. So for example, if you had 3 color map entries, one with the quantity set at 100, one set at 200, and one set at 300, where the color assigned to the quantity 100 was red, and the color assigned to the quantity of 200 is blue, all of the pixels in the raster that are 100 or greater and less than 200 would be assigned to red. Likewise, if the color assigned to the quantity 300 entry is, say, green, all of the pixels starting with 200 and less than 300 would be blue, and all of the pixels that are 300 or greater would be assigned to green. So you can think of it as defining color steps, with each step defined by the value of the color map entry quantity. You can see the difference between the smooth gradient visible using the ramp style and the uneven color assignments used in the interval style, where the colors are consistent until you hit the value associated with each of the color map entry elements. The values type for the color map is a third way of essentially selecting specific values that would be used in the display of a raster, but in this case, excluding all other values that do not exactly match those that are specified in the quantity equal attribute of each color map element value. So while it looks like we just have some specs on the computer screen, what we are actually seeing in this map are only those pixels that have values that correspond to the values that we defined for each color map item. Any other elements are not included in the generated map. You could think of this as a filter where you only display the pixels that meet a particular value condition. And as you might imagine, this would allow you to also create highly customized representations of raster data. Also, this allows you to provide very detailed classifications for data that represent categories of values. Say land cover, where instead of measured values like elevation or, say, pollutant concentration that may be more continuous across the landscape, you might have a land cover data set that uses 16 categories, as is the case with NASA's MODIS land cover product, where each of those 16 classes represents a different type of land cover. So here you could define a type equals value color map to assign your own custom colors to each of those land cover classes, while also assigning a label to each of those that might then be used in a map legend. As an example of what those map legends might look like, these are 3 map legends, each corresponding to the previous 3 WMS requests and map images published by GeoServer using those 3 different types of color map, where each of these is actually generated using another WMS request that we haven't previously talked about, which is the get legend graphic request, where you can see the basic syntax for that here, and at the bottom of the slide is a link to the GeoServer documentation for the get legend graphic and how it is implemented within GeoServer. So if you'd like to learn more about how to request legend graphics from GeoServer, I encourage you to visit that documentation page and learn more about this particular request. But looking here at these 3 map legends, we can see 3 things. First, that the first and default ramp color map, represented by the leftmost legend, is a continuous range of values where the specific values defined in the color map items correspond to the numeric values in the scale provided to the right of the color ramp. But you can see the gradations of color that have been assigned to the values in between those defined steps in our color map. That is in contrast to the colors that are assigned to the values in the center map legend, where these represent the color ranges from the lowest to the next and to the next category of values. So in this case, and to clarify this, it would be better to include the ranges in the labels that we're generating for an intervals type color map. But here we can see that the pale green starts at 0 and goes to any value that is below 1000. We can see the next brighter shade of green is applied starting at values of 1000 and continuing to any values that are below 1200. At which point we go to yellow, orange, brown, pale green, and then 2 shades of dark green. So each of these represents the range between the 2 color map item quantities that are defined for each class. And here in the default display of the map legend, you can see that GeoServer describes this as a color map type of classes, which is not consistent in terms of the terminology with the intervals type that is defined in the styled layer descriptor, but that corresponds with that intervals type. And then finally, on the right, we see the map legend that corresponds to the values type of color map, where it looks the same as the center one in terms of the color patches indicating discontinuous values between the specified classes. But in this case, it is the legend that represents the display of only those pixels that have those exact values that are defined there in the labels. And you can tell that by looking again at the color map type as provided in the map legend, where in this case, the map legend indicates that it is unique values. Again, not consistent with the terminology used in the style layer descriptor, but just something to remember, where the unique values color map type in the map legend corresponds with the values color map type defined in the style layer descriptor. We can also see in each of these map legends that the color map that is used for each of these is not extended, meaning that it is limited to a maximum number of 256 colors, as opposed to the over 65,000 colors that would be available in an extended color map. When considering the distinction between using an extended or non-extended color range for a given color map, we should think about the degree to which users will zoom into the map, where they might start to see visible banding of the colors, as you can see in this particular example on the screen, where I have zoomed into a particular area in northwestern New Mexico, where you can see the stair-step effect created by the smaller number of colors that are in the color ramp that was generated for this particular elevation model, and whether or not you want to have a more smooth representation for the values that you have in your map. If the additional cost in terms of file size and processing is worth it, then you may want to choose extended equals true. GeoServer uses a default of extended equals false, so that if you do not specify that an extended color ramp should be used, one will not be used, and the color ramps that are generated will be limited to 256 colors. In many instances, this is sufficient, but if you start to see visible stepping in the colors that are automatically generated for the display of your maps, you may want to choose extended equals true for a given map. That having been said, the current version of GeoServer that we are running on the class server does not currently support the extended color map option. So all of the map images that are generated, regardless of what you put in the styled layer descriptor, will be rendered as non-extended color maps. This has been resolved in more recent releases of GeoServer, so this is definitely something you want to keep in mind. It's just a limitation of the current server that we are working with, that is version 2.0.2 of GeoServer. Opacity can be defined at two different locations within the raster symbolizer. First, at the level of the symbolizer as a whole, where you can define the opacity of the entire data set that a given raster symbolizer refers to, or also within specific color map entry elements within a color map definition, where you can define at the level of each of those color map entries a level of opacity that ranges from 0 for completely transparent to 1 for completely opaque, with gradations in between. One of the interesting things that you also get when you define opacity for color map entries is that just as colors are interpolated between the individual color map entries for the color map of ramp type, the opacity is also interpolated between those values. So you actually can get graduated opacity for each of the colors that fall between your defined color map entries if you're working with a ramp type color map. These opacity values control essentially the degree of a background image as it would pass through the map image that is generated, which you need to think carefully about if you're going to be combining a raster in, say, a combined map service such or map client such as OpenLayers, in terms of how this raster that is being rendered with some degree of opacity might or might not combine very well with underlying data layers. This can be a powerful tool, but you need to be conscious of how it might play out in particular scenarios where your map service data may be combined with others. As I mentioned earlier, many raster data sets can contain multiple bands of data. And a classic example of that are photographic images. So aerial photography or other digital orthophotography typically consists of 3 bands, where those 3 bands automatically are assigned to the colors red, green, and blue, or RGB. But you may encounter data sets that do have multiple bands, but those bands don't necessarily or clearly correspond to red, green, and blue as you might try to visualize them using a standard color model that is typically a combination of red, green, and blue to produce a specified color. In those cases where the default mapping of bands from a multi-band raster dataset to either a single band representation, say a gray channel, or a 3-band representation using red, green, and blue channels in GeoServer, you can define how those bands should map onto those 3 channels, red, green, and blue. In the sample that I provide here, you can see that I am using the channel selection element, and within that, defining 3 channels: the red channel, the green channel, and the blue channel. And for each of those, I'm defining the source channel name, or in this case, these are the numeric identifiers of the 3 channels in a raster dataset. And to the red channel, I'm assigning channel name 3. The green channel, channel name 2, and the blue channel, source channel name 1. So if you've worked with 3-band RGB rasters before, you'll recognize that this is a reversal of the standard linkage between the channels and their colors. And this is done for illustration purposes here, but when working with multi-band images, you may have many good reasons for strategically selecting particular channels to be depicted as red, green, and blue. One common one being the selection of particular channels or channel combinations to be able to, for example, highlight vegetation or water within multi-channel, multi-band raster data. By strategic selection and assignment of channels and their mapping to these three color channels, you can generate representations of your raster data that emphasize particular features of interest within those rasters. Here is the illustration of what that channel selection example was that I provided on the previous slide. On the left, you see the standard and default mapping of channel 1 to red, channel 2 to green, and channel 3 to blue. On the right, you can see my modified mapping, where in this case, I assigned channel 3 to red and channel 1 to blue. Channel 2 remained assigned to green in both of these examples. So I just essentially switched the red and the blue channels. And you can see the effect that it has had in the display of this map, where the ocean areas that had previously been shades of blue are now closer to shades of red. And areas that had some red influence, say for example the western half of the US, are now more bluish as that red influence is now shifted to a blue influence. And you can also see how the areas of green, or at least strong green, have not been significantly modified as we didn't change that particular channel assignment. So the areas that were green in the first image are also fairly green in the second image. Another way to modify the image that is displayed through essentially through changing the colors as they're assigned to specific values is through the use of the contrast enhancement capabilities within the styled layer descriptor and GeoServer's implementation of those as a part of its map visualization services. 3 contrast enhancement functions are defined as a part of the styled layer descriptor and implemented within GeoServer. And they are the 3 listed here, where the histogram method essentially stretches out the pixel values so that an equal number of pixels from the map image fall into each color in the range of values. So this has a way of essentially flattening out the distribution of particular values so that then those collections of values fit into each of the colors in the range that is being used for the map. So if you have a range of 256 colors and you have a million pixels, you are then going to divide those million pixels evenly so that each of those bins that correspond to those 256 colors contains an equal number of pixels. The normalize function is different in that it essentially takes the minimum and maximum raster values and matches them to the minimum and maximum brightness values for the particular color channel that we are working in, but does not modify the distribution of pixel values otherwise. So essentially, this is a way to stretch the minimum and maximum values to stretch the distribution of raster values so that they correspond with the minimum and maximum brightness values in the appropriate color channel. This is a common method used in photographic imagery to provide the maximum contrast without significantly modifying the relationships between the different colors in the image. The third method is gamma, which is actually a method that takes care of either brightening or darkening by a specified factor. So while Normalize and Histogram do not require any additional information for them to modify the mapping of values to colors, the gamma requires you to provide a value that is used to scale the degree to which an image will be brightened or darkened. Where negative numbers for the gamma will typically darken the image, positive numbers will brighten the image. As we look at examples of these, here is a sample styled layer descriptor that we can use to then illustrate the specifics of each of these methods. So here we have a raster symbolizer with a channel selection block, as we saw previously from being able to choose our channels, but we've now added to each channel a contrast enhancement element, which in turn contains an element that defines the specific contrast enhancement method that we want to use. Where in this case, we are using a histogram contrast enhancement for each of our 3 channels. You'll also notice that in this case, each of these channels is defined in what you might think of as the natural order. So the red channel in this case corresponds to the source channel 1. The green channel corresponds to source channel 2. And the blue channel corresponds with source channel 3. So let's now look at what these different contrast enhancements look like in comparison to the base or unmodified image. Starting with Normalize, where you can see this is the syntax for defining the normalization contrast enhancement method, where you just specify a self-closing normalize element inside the contrast enhancement element. You can see in this particular case, and I should emphasize that it is this particular case because this will have different effects on different rasters. But here, since the source data that were obtained from NASA for the Blue Marble Next Generation, from which this layer is obtained, was previously normalized in that NASA already has applied a normalization to the image that they are then publishing, you can see that there is no visible difference between our normalized image and the original image that is subject to just the straight display of the unmodified RGB pixel values. In contrast, we can see here the results of the histogram contrast enhancement, where again, this is just the simple inclusion of a self-closing histogram element within the contrast enhancement element, where then GeoServer calculates the redistribution of the pixel values across the range of colors that are to be displayed. And you can see here quite a marked difference between the original image on the left and the histogram enhanced image on the right, where we essentially have a much wider range of values for say, for example, blue, where we have now a range from very light blue to very dark blue, and very light green to very dark green. And with red contributing to the other elements, but also ranging from very light to very dark, with those values being now distributed equally and uniformly across the range of colors for each of those color channels. So you can see this has had a significant impact on the image on the right when compared to the more natural color image on the left. Finally, we can see the effect of the application of a gamma enhancement, which here is represented by both the gamma value element and a value that it contains. So you can see that in contrast to the previous two self-closing elements that we worked with, the gamma value actually contains a value that you need to provide, which in this case is 0.5. So we have an opening gamma value element, a value that we provide, 0.5 in this case, and then a closing gamma value element, all of which is contained again within the contrast enhancement element that is assigned to each of the channels in our sample. And you can see the change that has had, again with the unmodified image on the left, and then the gamma enhanced image on the right, where you can see that overall the entire image has been brightened through essentially the brightening of each of the individual channels that are contributing to the image. Similarly, if we had used a -5 value, the entire image would have been darkened relative to the original, with that darkening defined by this negative gamma value that would be defined for each one of the three channels contributing to the final map image. So with all of that, let's take a quick look at GeoServer to see what these styles look like within GeoServer and how you can preview their effects and apply multiple styles to a given layer so that you can experiment with different raster styles. Here we are in GeoServer, and we can look at the available styles in the system by clicking on the Styles link. And at this point, we can see that we have over 123 styles defined within the GeoServer. And I want to concentrate on a particular set of styles for these examples. So we will first look at the digital elevation model styles that I was demonstrating as a part of the lecture. And those are all prefixed with DEM. So I can type DEM in the search field here and hit return. And here I will see all of the styles that begin with DEM. And I can then look at the definition of any of these styles, where this DEM style here is the original one that I created previously for simply displaying the digital elevation model that was added for the class. And you can see that the color map does not have any particular type or extended value assigned to it, but it does have a number of color map entries that define the specific raster values that I want to use to anchor the color ramp that is automatically generated for this DEM. If I instead look at my interval style, which is based upon and actually copied from that base DEM, you can see here the only change that I've made is to this line where the color map is defined, where I added a type equals intervals to that particular style. And when I made that change, and in this case I made that change right here in the editor, I validated it. So I hit the validate button and saw that there were no validation errors as indicated at the top of the window, and then submitted it. This then takes me back to the full list of styles so I can continue working with any other styles that I would like. I repeated this process for multiple DEM styles and also new styles that apply different contrast enhancements. So once I had created those additional DEM and contrast enhancement styles, I can then assign those to my layers so that they are available for each of those layers. So if I click on my layers here and open up, say, my the National Elevation Dataset Northwest Quad for New Mexico, I can click on the layer name and then click on the Publishing tab. And once there, I can scroll down to the area under the WMS settings where I can see what the default style is. In this case, the default style is DEM-ramp, which you might guess is an explicit DEM style of type ramp. But then we can also go down to this list of available styles and assign additional styles to this layer that would also be advertised and supported by this layer. And in this case, you can see I've already chosen a number of styles from this list of available styles and copied them over to the selected styles list. And to add one, you just click it on the left and then click on the arrow that adds it to the right. Likewise, if you want to remove a selected style, you just select it on the right and click the arrow that moves it to the left. GeoServer keeps track of which styles are available and which ones have been selected, so as you move them from one side to the other, they're automatically removed from the source and added to the destination. So once you have added the selected styles to your particular layer, you click on Save, and those styles are now available for use in that particular layer. And we can verify that by going into the layer preview and choosing the layer that we would like to view our test our styles in. So if, for example, we look again at this Northwest Quarter layer and we open up the Open Layers preview, we can see here the default style. I can click on this Options Toolbar button here to toggle the options open, and I can go to the Styles menu and choose from the list of all of the available styles that have been assigned to this particular layer. And so I can then choose, say, the DEM interval. And you can see that this is what that interval style looks like. Likewise, I can choose value. And this is that sort of smudges on the screen representation for the limited number of classes that we've defined for this DEM. Or we can choose DEM ramp, which is an explicitly defined ramp type as opposed to the default that is associated with the default ramp type that is automatically assigned to any layer that does not specify the type that should be used. Likewise, we can look at, say, the Blue Marble Next Generation 8-kilometer worldview. And we can zoom in, and this is, as is always the case, the default style for this particular layer. But I can then open up my options here and choose the other styles that have been assigned to this. And you can see these are styles that I have previously defined that were used in the lecture that correspond to the different examples. So for example, this is the reversed color channels where the red and blue are swapped, keeping in mind that the source data remain unchanged. Here is the normalized representation of those data. Again, not significantly or visually different from the original data, as that the original data were already normalized before they were downloaded and added to the system here. Our histogram style. And again, then our gamma style. So these are all styles that are available right now within the class instance of GeoServer. And I invite you to look at them and experiment with them and look at ways where you might be able to apply these styles or styles like them in the work that you're doing with GeoServer. So with that, I invite you to continue your experimentation with GeoServer in both evolving the way you represent your vector data and now your raster data, in developing a comprehensive collection of OGC services that you can then integrate into web mapping clients.